that you come and get this thing done so we can have a good, relaxing Halloween weekend. All-day weekend and then holiday weekend? Go wrong. All right, so reading guide 14 questions is what I'm starting with. Reading guide 14 questions.
So all the variables except for volume are directly related to pressure?
Yes. Yes. Good job, man. All right, that was a statement. Do we have any questions on reading guide 14?
No.
Speak now. You guys got 100% of it done? Yeah? What do you need? Concept. Okay, hold on. Let me look at reading guide 14. So I like to have at least one question. There's only 8. Woo! Give me a question. Fourth one. What are the conditions that define an ideal gas? Okay. We're going to go over this more so on Monday or Tuesday. Be a man. It's all right. Whenever we have ideology, who feels like they're my ideal student? Perfect in all ways, always turning their homework, participate in class, are really excited about science, going to grow up and donate back to my classroom. Yep, okay. So, ideal gases have these special characteristics as well. They're not like ideal as in perfect. They have different properties, like they don't interact with other gas particles. Their speed that they travel is directly proportional to their energy, or their kinetic energy, or their temperature. So very, very specific characteristics that indicate that it's an ideal gas. Specifically, they don't interact, and they have negligible volume, and they move at the rate of their temperature. So things like that are the conditions that define an ideal gas. There are a couple of other things, but we're going to talk about that more in depth on Monday. Okay. More reading guide 14? Nay? Yay? Yeah.
Number 8.
Write down the important gas formulas. How about that foldable? How about that foldable? You got all the formulas in your foldable, right? Have you made progress on your foldable? Okay, well, we're going to make sure you make progress on the foldable today. The foldable that I forgot to take up, the types of chemical reactions one, that's going to make sure you put in the box before you leave me today, okay? Just put it on your desk, and it'll remind you to kind of put it in the box, but not just yet, because I want you to make sure you know what you're writing here. So the gas foldable, though, you will make progress, and you'll have a lot of it hopefully done today. Because I do believe if you introduce yourself that way, every day, everything on today's notes is going to be very easy. Okay, reading guide 13 question. I mean, my bad. Concept 13 question. Do you remember what it is?
When the physical state of
Okay. Tell me what an E-curve looks like. E-curve, how does it start with? Starts with a slant or a plateau? Slant, plateau, slant, right? Okay, so solid, liquid, gas. Where does the phase change go? Here? Or the flat, right? And what is the axis over here, the y-axis? Temperature. So if you guys are telling me, as far as the blue marker is kind of hard to see, if you're telling me the phase change occurs here, what's happening to temperature at that? Nothing. No temperature. So the point of learning how to read these is to realize that during phase change there is 0 temperature change. But there still is heat being added, right? So this is like over time, heat is added. And that heat added does not relate to temperature change. But what does it relate to? What is it being used to do during that phase change? Specifically solid to liquid. Okay, you know it's melting, and so the heat is being used to give them more energy to kind of separate themselves from one another, overcoming the intermolecular forces that we talked about yesterday. It was a very specific explanation. Another question? Any more concept 13 so far? Okay, on your desk on that worksheet you did yesterday, and your concept 13 that you started, and then go ahead and pass up reading guide 14. All right, so all at once. So passing up reading guide 14 to math. Reading guide 14 to math. So up and over.
And are you just checking the other ones?
The other ones are going to be on your desk. You're going to check throughout the day.
Right.
Okay, so you're writing down some variable information. Can I scroll down a little bit? Just a little bit. Just a little bit. Just a little bit. Hello there. Is that good? Okay. Who's done with this already? Okay, cool. Nobody. Great. No, it's really great. I think you're good. first thing, which of these units or variables seem new to you? Anything new that you don't feel comfortable with? Maybe that you've not seen before? Oh,
What is K?
the mercury stuff. Okay, so what we're going to start talking about is units of pressure. Well, when we talked yesterday about units of pressure, what pressure unit do we really, just the one that we refer to? We said we live at this 1 atmosphere, so we live at 1 ATM. That's generally where we say that we live. It's not exactly right, but atmospheres is what we're really familiar with. But that's equivalent to any of these other pressure units because, you know, everybody's got to put their name on something. Okay, so guess what? KPA is kilopascal, some guy named Pascal, right? And then back in the day, they used to measure pressure, and they still kind of do, with barometers that have mercury in them. And they literally measure the height that the mercury is a column of mercury, measure the height of it in millimeters. So they were not creative. They're like, hey, we're at 10 millimeters of mercury for our pressure. It's little millimeters of mercury. So mmHg is millimeters of mercury. So it's just that these are all just pressure units. And there's another one called bar. There's another one called torr. So there's some other ones, but those are the three we'll really use. Yeah.
In a minute, scroll back.
Mm-hmm. So I just want to make sure that you do see that there are lots of units, and so you need to learn how to convert between them. But if these are all equivalencies, that means that any of these you can convert to any other ones by knowing these numbers. So you should know 101.3 and 760 pretty specifically. So if I wanted to say, let's say we were on Mount Everest, and what was that atmospheric pressure we used yesterday? 0.5. So take that 0.5 atmospheres, and I want you to convert it to millimeters of mercury. You can probably do it in your head. What is it? I want you to take 0.5 atmospheres and convert it to millimeters of mercury. So if 1 atmosphere equals 760, so half that, 380, yeah, 380 millimeters of mercury, right? But I like to show my math for it, right? So I like to do the whole dimensional analysis. Millimeters of mercury over 1 ATM. So what cancels? ATM, so it's 0.5 times 760, which is exactly what you just did in your head. It's just showing out the math for it. Okay, keep working on here for a second. I have like 3 demos I'm going to do. Okay, let me get my little box. I might just go back there. Everything I need is back there. So I'm going to move back here. So, some of these eggs have seen better days. We're going to work with it though. Alright, so turn around this way. Let me start with this. This is one of my favorite steps. And so it's relating to vapor pressure. What is vapor pressure? Pressure of vapor, right? Okay, there's vapor in each of these jars. So you can do volumetric class. You cannot see them because they are vapors. You can see some of the residual liquid that's still there. You can see some of the salt that's in there. The salt is not sodium chloride. The salt is just an ionic compound. So this is actually a boric acid. So, yeah, and I was a chance and I can't tell the lecture. Okay, so here we go. Focus work. May not give enough time to do this yet. That's, yeah, so you can see it. It wants to, but I may not give it enough time because I just prepped this. It must be a little while to go for it. Alright, I'll come back to this. Try this. Yeah, like that. This one's big. actually bark. They make really loud noises. Cool. Okay, so that one then. Alright, can we put the lights back on for me? So next we have you guys ever seen the egg in the bottle experiment? Some of you guys have, some of you are like, no, this is magic. She speaks of. So, see that it did not fit in the bottle, right? It's not going in. How can I make it go in without touching it?
I was going to say,
Eat what? Glass? How do you eat the inside of the glass? Does it have fire? What if I wanted to go in there but upside down? I can't touch it. Make it a vacuum. Alright, here we go. So, let me get my hand then. Candles.
It's your birthday.
Keith's okay.
What a beautiful cup.
Keith's okay. I gotta keep it on the DL. I get Keith on it.
I have a thing first. So here's my little egg. Happy birthday. So I'm not going to switch it up, okay? I'm just going to stick it in here. Just gotta kind of latch on. Defying gravity. But where is it? Like what? How would actually happen? How would that happen?
You need oxygen for the play. You decrease pressure on the inside and then increase pressure.
Right. So the atmosphere pressure is pushing on you right now. You feel it? It's pushing on you. Okay? We're pushing back too. So we're at this point where we're pushing back. Right back down here. But the atmosphere is pushing on everything, and it doesn't push unidirectionally, it pushes in all directions. So it pushed the egg up there. It didn't suck it up there, it pushed it up there. Okay? So that lower pressure system inside, how did that become a lower pressure system? Because the what? The candle. What was the candle? What kind of reaction was it causing? Combustion. So it consumed all the oxygen. It made some carbon dioxide and water vapor. You can probably see a little bit of water vapor around. They consume the oxygen, so there's less gas pressure inside. Less gas pressure because pressure system. High pressure system pushes up. Okay, how would I get this out? Heating the flask, and what would happen? So heating the flask right here would do what to the gas in here? Okay, make it expand, and that would create a high pressure system, and then it would push this out. Yeah? Okay, I'm not going to do that. I might get a high pressure box burner because it takes a while to come through. Okay, so let's go ahead. Let's go back here. Okay, so do anything with brain. How can we find those? Alright, and find a lab station. Like, this is a lab station. This is our station here. This is a lab station. Alright. Let me take the lid off, guys. Alright, we're gonna be back here for just like maybe 10 minutes max, okay? Honey, grab one for like grab one from start reading the sheet at your desk. Start reading the sheet at your desk. Question can. Yes. What is the Okay, guys, here's what I want you to do. Listen to me. 5, 4, 3, 2, 1. Okay, you should be at a station where either you have cup and a index card or a soda can and a hot plate. I want you to try to do both of these in about 10 minutes. So what are you doing on the hot plate station? What does it say to do? Okay, add a little bit of water to the can, and then what? Okay, so that means you probably want to go ahead and unwrap the hot plate and get it boiling. How will you know it's boiling? You'll start seeing steam come out. Steam is gas, right? We're talking about gases today. Okay, and then what should already be set up before that starts boiling? A beaker of ice water. So our ice here, now we'll come and distribute it around. The beaker should be pretty much full of water and ice. Okay, so like half water, half ice. The other group can work on this. This is really easy. The water in the cup one, that's just to kind of while it's waiting, you guys can do that while it's heating. So go ahead and hook it up. Water in the pan. Get your beaker tongs out. Get your tongs Alright guys, I can tell you when to turn the can over. And then I guarantee you, nobody's ready to turn the can over in the ice yet. Put it back on the hot plate. Put it I promise I'll let you know, because I want you to have a good experience. Flip it.
I would do it over the
Oh yeah, you guys are good. Okay, so one person who's ever first, the next one, you're going to literally. What happens with the water? Okay, so take the here's what you should be looking for. I want you to watch this station. You can see, and you can hear it. Hear it boiling? That's when you know you're ready. Okay. 3. Here. I want you to flip it, and then flip it. Okay, 3, 2, 1, go. Turn it, now. Okay, that's all. All right, I want everybody to raise their hand in the next minute, and then we have to kind of go back and clean up your stations, put your cans in recycles, throw away your index cards. I'll see you back in front in a minute and a half.
You have to wait for it to
Okay, guys. If we have time, we'll go.
I'll get some.
I thought you Okie dokie, guys. All right, let's go, folks. Let's go. That's all. Oops. Okay, so I'm gonna go back up here to the front. That's not what I need. Okay, so you can see that we're talking about gases. We're talking about pressure. We're talking about the pressure and volume and temperature interactions and what does it do to a gas, right? So in the crush the can one, what was the very first thing you did to the water? Hey. And then what happened to it?
Started to steam.
It turned to steam. Okay, so we made a gas, right? We made vapor. All right, and it's taking the space of its container, right? It's all over on the inside of the container. It's even coming out of the container. And then, what did you do? You cooled it down really fast by flipping it. But not only flipping it and cooling it, but you flipped it and allowed you block its escape route, right? You put the hole in the inside of the cold water. So then what automatically happens to the gas? It condenses very quickly, and what else happens to the can? How does it? How does it do that?
Somewhere.
Okay.
Thermal reduction or something.
I mean, maybe thermal reduction, but I'm going for more of the pressure argument that we had here. So,
Was it something like the pressure on the outside was more than the pressure on the inside?
because once you covered the hole and there's no more gas that can get in or get out, the gas that's in there condenses. Well, then all of a sudden, they're not hitting the sides of the container. They're not causing any pressure. Not causing any pressure means pressure goes down. So then who wins? The atmosphere wins, and it crushes it, right? So that's how that works. And then with the cup one, what's up?
Because like you know with like soda how it goes like that makes that noise. Like if it were to happen with cans and like it would have the same pressure in you and like if a can had a screw top, would it like crush somehow? Or would it not be enough pressure?
No, because it wouldn't be. Because that once you have an escape route, there's gases that can mix and they can go in and out.
Right.
So yeah, it's more about the closure, the closed container, than more than the pressure. Okay, but with the cup one, what happened? Okay, but how did it create a suction? Like what's the relationship here with the volume of the gas and the pressure? Any idea, or is it magic? It's magic, obviously, right? So we've got a system where you put gas above the liquid, right? You put the lid on it, the index part. You pushed a little bit, so you made it have a little bit more pressure on the compressed on the inside. When you flip it upside down, that there's actually like a vacuum kind of on the inside, and that's why it holds the index part to it. And that eventually does fail because the moisture, the ring that gets kind of moist and it doesn't hold it very well. It's not a good seal, but you can kind of see how that works. You can do that trick, Halloween parties. Hey guys, what I learned? It's not science, it's cool. Okay, so we're going to talk a little bit more about gases now. We have a couple gas laws we're going to consider, but I want to make sure we're okay with pressure first before we consider the gases. We're good with we know what our pressure units are. Now, what's causing pressure? Specifically, you should always mention collisions with the container wall. That's what's causing pressure. That's it. Nothing crazy. Collisions with the container wall. Second, whenever we measure volume, generally we're going to be always converting to liters, but occasionally we will talk about it in milliliters, specifically in some of our questions, like on our problem sets. Temperature, we always convert to Kelvin, without a choice, okay? But I'm really nice, and I give you Celsius first, so you can have this chance to practice converting to Kelvin. Because I love you, and I want you to be really smart with like how to add 273, right? Okay, so I will always usually give you in Celsius, and your job is to convert to Kelvin, 100% of the time. But what is temperature? Temperature, this is a definition, is the average kinetic energy of the substance, right? Average kinetic energy is energy of motion. So tell me, if I increase temperature, what happens to kinetic energy? Okay, so what happens to the gas particles? They move faster, and if they move faster, they probably are going to do what with their container wall more often. Collide, and then what could happen? The pressure could go up. So you see this domino effect. So you have to understand the molecular motion and what's happening to understand the pressure changes and the volume changes and so forth. And then whenever we denote moles of a gas, we always call it N. It's the N number. So it's just another variable you need to be aware of. Okay, so let's talk about some of those gas laws. And if you have your foldable, or if you want to kind of jot down what's in your foldable, that might be smart, right? Kind of kill two birds with one stone. Tell me one of the first gas laws that was on your foldable. Boyle's law. Boyle's law is the relationship between what and what? Volume and I heard it. Pressure. Okay. So this is the relationship between volume and pressure. So you got your box of air. Yeah.
Did y'all make this foldable Wednesday?
Maybe, yes. If you don't have foldable paper, then you'll get foldable paper. Not so much. Yeah. But I'm hoping that you can get some of it done today. So right now, just take notes on a piece of paper and then you'll transfer. Okay, so I'm starting with Boyle's Law because that's what you guys started me. It's the relationship between volume and pressure. So you have your box of air, increase the pressure on it. What happens? Okay, so is this a direct or indirect relationship? Okay, you just told me increasing pressure does some damage to the volume, right? It smushes the volume down, and so it's going to be a decrease in volume, and vice versa. Decreasing pressure would do what to volume? Increase it. So we need to know this is an indirect relationship. Okay, indirect relationship, and so there's a formula for that. Who has the formula for me? They're next to each other. So P1 times V1 equals P2 times V2. You need to know this, and you need to know it's called Boyle's Law. And not only what it is, but it's called Boyle's Law. Okay, so this is indicating to you that indirect relationship, because if I had a scenario that I started off with a specific amount of pressure, and then I changed the pressure, so my specific initial pressure is P1. The pressure I changed it to is P2. Well, with those pressure changes, there's going to be a volume change in an indirect relationship way, in the inverse way. So, what do you notice I'm not mentioning here? What variables? Temperature and amount, moles, right? So what do you assume about those? Are they changing? No. Okay, so temperature and moles are constant. Okay, and then if I had to graph this, and I had to graph like the relationship, and it's an indirect relationship, what would you imagine the slope would be? Positive or negative? Negative. Indirect relationship means opposite, so it's a negative slope. So this would be pressure and volume. Yeah. So if I have a low pressure, I have a high volume. If I have a high pressure, I have a low volume. Okay. It's actually kind of more of a curve, but I just wanted to indicate the slope to you. I'll draw it more accurately for you. It's kind of like that. It's not a huge curve, but it does have a little bit of hyperbolic nature to it. Okay, Charles's Law. I'll tell you a little story about Charles, and then you tell me what variables are involved. He went to Virginia Tech. End of story. Volume and temperature. Okay, so volume 1 over T1, temperature 1, is equal to V2 over T2. Okay, so we kind of just talked about this. If I increase the temperature of my gas, what do they do? Increase the temperature of my gas. Now tell me in reference to what their motion, what happens to their motion? They speed up. And if they're speeding up, they're moving farther apart and farther apart. And so then what happens to the volume? It grows. It gets bigger. So this one, when you increase the temperature, they move faster. And before I move on from there, what variables do you see that are constant here? Temperature and volume are moving. They're variables that can change. So N and P are constant. Okay, so tell me, if P has to stay constant, and you increase the temperature, what did we just talk about when they increase the temperature? They're moving, and what are they doing with the container walls? They're colliding. If they're colliding a lot, right? They're colliding a lot. What is automatically going to happen to pressure? It's going to increase. Well, we're not allowed to let it increase because pressure is constant. So what do we alter to alleviate that pressure? The volume. You increase the volume, because when you increase the volume, they've got more space to play. So do they hit the container walls as much? No, because they've got more volume to hang out in. So increasing pressure actually causes increasing temperature actually does cause an increase in pressure, but we counter that by increasing the volume. And so that's why we always say increasing in temperature would cause an increase in volume, because we cannot allow the pressure to increase due to Charles's Law. So scenario 1, V1 T1, scenario 2, V2 T2. There's always going to be 2 scenarios given to you. But what I would do for you is I would maybe give you 2 volumes in one temperature, and your job is to solve for the other temperature. So I'll give you 3 variables out of 4. Okay, so then this graph would have what kind of correlation? Positive or negative? direct, right, positive correlation. So increasing temperature increases volume. Okay, so that's B and C. So Boyle's law and Charles' law. Going back up here, Avogadro's law. Avogadro's. Who's got me here? It is related to the man, Avogadro. Avogadro, that's his name. Did anybody have this on their folder yet? No? Okay. What if I told you it's between moles and volume? Let's kind of make a guess here. If I have a balloon, and I put moles of something, and I put like a specific number of moles in there, the volume is yay big, right? If I add more moles, it's going to increase. So this one is similar to Charles's. N1 over V1 equals N2 over V2. What's constant? Okay, so temp and pressure are constant. What's up, Carolyn?
This.
Okay, it's not one that we use a ton, but we need to know the relationship. So that's maybe why I forgot, because we have more laws to talk about another day. Okay, so if T and P are constant, the reason the volume is increasing, let's kind of go through that whole scenario domino effect again. I have a balloon, it's yay big. I put more moles in it. What's going to happen to the pressure at this size? Increase? Is that what you said? Why? More collisions with the container wall. There's more stuff in there hitting the sides of the container. I cannot allow the pressure to increase. So what do? Increase the volume to give them more space to play, less collisions with the container wall. Constant pressure. So that's why when you increase moles, that's going to cause an increase in volume. So that's, again, a direct relationship. And then, any of the graph, positive or negative? Positive correlation, so increasing in moles increases in volume. Okay, so we got Avogadro's, here's the ABCs, Avogadro's law, Boyle's law, Charles's law. All right, so we got two more to talk about, but they're just variations of some of these. They're more like combinations of these. So I'll start with Gay-Lussac and I'll go to combined. So Gay-Lussac is going to be a different relationship. Yeah. This one?
Yeah.
There you go. Okay, so we've compared N and V, P and V, T and V. What have we not correlated yet? P and T. Okay, here P and T. So tell me, if I increase the temperature of a gas, what did you say it did to the pressure? Increased it. And that's the correlation here. Increase in moles, I'm sorry, not moles. P1 over T1 equals P2 over T2. Increasing in temperature increases in pressure. So it's a direct relationship again. This is called Gay-Lussac's law. Increasing in temperature increases in pressure. Direct relationship. You're kind of seeing the flow of this. You're looking for relationships. You're making a graph on it based on if it's a positive or a direct relationship or indirect relationship. What's constant here? Constant N and
V.
Volume V. Good. Okay, combined gas law. Guess what it does, guys? Combines all of them except for the Avogadro's. So I want you to think about how would you combine Charles's law, Boyle's law, and Gay-Lussac's law. And what would it look like? P1, V1, I hear you, because that's Boyle's, right? And T1 goes on bottom? Okay, that's it. But then you replicate it on the other side too. P2, V2, and T2. And you're assuming the what's constant? Moles is constant, right? So really, if you know the combined gas law, you know every law. You know them all. So if I did tell you that, maybe temperature was staying constant, then what would you wipe out? You just wouldn't put the denominator. If I told you that pressure was constant, you would just ignore the P's. You just totally take them out, and that would be Charles's law. If I told you volume was constant, you take out the V's, and whose law would that be? Gay-Lussac's. So if you know that one, you know them all. Yeah.
Can you go back to Avogadro?
Hmm? So we're going to use these, and I'm going to kind of go through a little bit more on pressure before we do them, but we'll be practicing, and you'll really like this. This is just algebra. Rearranging, finding x. Okay? But the only thing is, you got to make sure about your units, because if your units are not the same for like both pressures or both temperatures, then you won't be able to cancel them out, then you got problems. So look at, I'm going to come back to this pressure gauge in a second. I have some pictures for you. I'll show you in a second. This one right here is, I think, the first one on your worksheet I gave you yesterday, 1 through 16. It's on the back of the phase diagram one. So I couldn't take it out because you needed it today. You got it? The first one. Yeah, first one. Okay, so this one you will not be able to show the work on that paper. It's too little. So go ahead and make a sheet of paper. Call it Gas Law Practice 1 through 16. It's on. So here's your worksheet from yesterday where you had all your practices. On the back of it, we have some gas laws. Perfect. I think we will finish this in class, guys. So whenever you do a problem, I want to see your givens and I want to see your setup for your formula that you're going to be using. And this is going to protect you from yourself, because sometimes you will get a little lazy and you'll make a mistake. So I'm trying to protect you from the laziness that will settle in. All right, so we have 700 millimeters of a sample of hydrogen gas. What variable is that representing? Pressure, right? I'm going to get my pretty pen. Okay, P equals 700 millimeters of mercury. This is me setting up my givens. You will do this, every single one of us. All right, it has a volume of 500 milliliters. Volume equals 500 milliliters. And I'm putting these decimals here because that actually means something in terms of sig figs. How many sig figs are the first number? 3 sig figs, second number. 3 sig figs, okay. So the pressure has decreased to 538. What will the new volume be? So you'll realize again it's giving us second pressure. I wonder why. 538 millimeters of mercury. And then what's my question? V is question mark, right? So you'll notice that these two here were given as a collective pair of information, right? So they have to stay together. They are P1 and V1. And then what is the second? P2 and V2. Whose law is this? Boyle's law. So right now you've already written down your givens and you've established your question. The second thing you do is go, which variables are they and whose law is it? You said it was Boyle's law. And you don't have to write out Boyle's, but what I want you to do is write out P, what's the formula? Times V1, right, equals. So I want to see that, something like this. But I always like to, before I plug a single number in, I like to rearrange my variables so I can just plug, calculate, done. Okay? Rearrange these, or what would I do to this formula to solve for V2? Divide by V2, right? So I'm going to assume that we're okay with the math. But I want you to, you don't have to show that step necessarily, but I'm showing it for you now. So what I have is V2 is isolated, so V2 is equal to this. So V2 is equal to P1, V1 over P2. And so I literally do this every single time. I'm an adult, I know math, but I'm going to do this every time just so I don't mess up. Because you can easily put the wrong number in the wrong spot. So then P1 is what again? 700 millimeters of mercury. V1, 500 milliliters over 538. Okay, so before you calculate, let's just think about the concept, like what actually happened here. What happened to pressure? Okay, so have your box of air, right? You decrease your pressure. What should happen to your volume? It should expand. So what should this number be? Higher than what? Than V1, right? So let's say 600-ish. Let's see what it is. 650. So V2 is 650 point what? Okay, so I'm gonna stop there. And then how many sig figs should that be at? 3. So round that to 3. 651 milliliters. This is the work I would like to see. Okay, it will help you. This will be a fantastic test grade. Gas laws are really actually pretty easy. But I want you to notice that I before I really moved on, I made sure my millimeters of mercury were the same, so I could cancel them out, because the only unit that should be left is milliliters, and that's where the volume is in. You should know your variable and the unit that it should be recorded in, just to verify you set it up correctly. Yeah.
Can you explain again the box?
So before we actually calculated, we just looked to see what would have happened, right? So we went from P1 to P2. Well, we had originally some volume, so we had 500 milliliters of our volume, and we had a pressure of 700. But when you decrease the pressure, what happens to your volume? So you relieve the pressure so the volume gets bigger. So then we kind of just estimated, we're like, oh, it's going to be bigger than 500. It's going to be maybe 600, 700 milliliters. And so then we actually calculated and verified. So it's like pat on the back because we estimated it correctly. Okay? Can you guys go ahead and start Boyle's Law? What I would do is leave some space, try one from Boyle's Law, Charles' Law, and so forth down that section. And go ahead and check your answers. Do you guys see the answers on the other side? Yeah, you see the answers on the other side? Yes? Okay, so check yourself as you go. So let's do one from each section for now, and then we'll kind of stop and recap. Yeah, you definitely need a calculator for chemistry. You may have noticed this. I hear you. I'm going to come and bother you and see your homework as you go. Oh, I'm going to pass out candy first. You guys are my secret checkers. I don't hand out candy to me children. Alright, so I'm going to come by if you would like a piece of candy. Just take one because I do have a fourth period. And they won't kill me if they don't have candy.
That's basically a York.
Right. Eat candy and do chemistry. You can multitask.
$30.
Eat candy and do chemistry. I'll take it back from you. Induce food. Induce food. If you are having problems on how to convert between different pressure units, let's say you're given 0.9 atmospheres, you have to remember the equivalencies of 1 atmosphere is equal to 760 millimeters of mercury, which is equal to like 101.3 kilopascals. Those are all equivalent, so if you need to convert between them, then you just pick 2, put them as a conversion factor, and move on. So if I wanted to convert to kilopascals, what 2 conversion factors would I choose? Or 2 units would I choose? Kilopascals and atmospheres, right? So I have to get out of atmospheres, so I have to put 1 atmosphere on the bottom. I want to go 2 kilopascals, so put that one on top. And that allows me to cancel out atmospheres and make like 99 kilopascals or whatever this answer is. You can do that with anything though. But the hard one is if you're going between like kilopascals and millimeters of mercury. So if you had 700 millimeters of mercury and you wanted to go 2 kilopascals, you got two numbers, two bigger numbers that you have to consider. You're going to put it here, but what number goes on top? If I said I want to go 2 kilopascals, that one goes on top. So 101.3 kilopascals would go on top, and then 760 millimeters of mercury would go on the bottom. And then the millimeters of mercury would cancel, but you'd still just have to calculate out 700 times 101.3 divided by 760. Yeah. So sometimes if your pressure units between P1 and P2 are not the same, you have to convert so that they are the same unit, and then you can plug them in, and then they will cancel. And we also have another eureka moment. Before you can even touch like the calculator and put something in, you need to convert Celsius to Kelvin before you put it in the formula, before you put it in the equation, whatever you want to call it. Okay, so I'll just look at a couple pictures, and you might need to sketch some of these. So, oh, I skipped the barometer. Barometer. All right, so here's what a barometer looks like. It's kind of hard to see. And you might be able to squint your eyes and turn your head to the side.
Oh.
Squint your eyes and turn your head to the side. You see it kind of looks like a U, or an upside down U. So the pressure can come in here, the atmospheric pressure, come in here and here. And there's a gap, or there's a piece of glass. The pressure travels all the way up here and in here. And then there's this second pass. It's kind of hard to see. Second pass, and there's mercury in there though. You can see it's like a ruler behind it. So they literally measure the millimeters of the height of the mercury, and that's how you get millimeters of mercury. It's not real fancy, but we don't use mercury a whole lot because it's toxic. So we're going to be using these lovely images that Enlo has drawn, like this. This is called a flask. You see it? It's a flask, and this flask has gas in it. P gas specifically. I'm going to turn the lights back up a little bit. You want me to draw that flask? Draw yourself a sketch here. And this flask, just indicate that for you so you remember it's a flask. It has gas in it, and it's going to be connected to this thing called a U-tube. It's not the U-tube, it's just called a U-tube because it's a U. Okay, so whenever this pressure inside the flask builds up, where is it going to go? To the U-tube, right? So it's going to, they're bouncing around in here, it's causing pressure. Well, they're going to come up here, they're going to bounce around. So I just draw arrows to represent it, moving. So P of the gas, the pressure of the gas is moving, and it's going to start to push on this mercury. This is pink mercury, okay? So this mercury, it's liquid, and it can move back and forth, back and forth, back and forth. Well, you can see it's open on this side. What's out here that could be pressing down? The atmosphere, right? So P of the atmosphere, ATM atmosphere, is going to push down here. So P of the atmosphere is pushing down the liquid, and the P of the gas is pushing down the liquid, and it doesn't move. What can you conclude? The gas pressure equals the atmospheric pressure. They're equal in pressure, because neither's winning. Neither's pushing the mercury to the left or to the right. So that's something that we're going to be kind of be expecting that we can interpret from like a lab situation, but we'll be using water, not mercury. Fun, I know. So in this case, if the gas won, if the gas had a higher pressure than the mercury, what would it look like? So like this, right? So I'm going to kind of indicate that here by maybe just erasing some of this and drawing it up some more. So it would be up here. Okay. So P of the atmosphere, you would conclude that P of the atmosphere was greater or lesser than the P of the gas? P of the atmosphere? You just told me that the gas is pushing itself up all the way over here, right? So this is caused because the pressure of the gas is pushing it down. So the P of the atmosphere is less than P of the gas. But by how much? This is mercury, right? Whatever this is in terms of millimeters of mercury. We can actually measure that with a ruler. If it were mercury, measure with a ruler and find the millimeters it's worth. So I like to call that change in height, because it's a change in like millimeters. And you could then say the pressure of the gas, move that right there. You could say the pressure of the gas is equal to the pressure of the atmosphere plus the height difference that we can actually use a ruler and measure it, and this would be millimeters of mercury. So equipment, you put stuff in there, you can have the gas push things around, and then we can actually conclude a lot about like the differences in pressure. So we might have one with the YouTube, but more than likely we're gonna have one with this. What is this?
Box there.
So beaker. What is this? It's upside down.
Oh, good.
Graduated cylinder. Yeah, you can see it. Yeah, let's make a graduated cylinder. It's upside down. Use your imagination. Because they love each other. No, it's because I don't have like we have these things called udiometer tubes in AP. I don't got enough. I got like 5, so we have to use graduated cylinders. It's just like poor man's udiometer tube. Okay, so we will have a beaker here. It will have water or liquid in it, right? Whenever we make a gas, we're actually going to light something on fire underwater, and it's going to bubble up and make gas, and it's going to make gas, and the gas is all going to go up there. So this stuff up here is P gas in this case. That should not be all the way purple, but it is. So that's P gas. What's out here? P atmosphere, right? What is P atmosphere doing to the water? Okay, it's what? It's putting pressure on it. It's pushing on it, right? Well, if P, the atmosphere, is putting pressure on it, it's going to put pressure on it like this, and it might even cause the water to move up into the graduated cylinder because it's pushing it to the next location, right? Well, there's gas up here, and I'm actually going to erase some of those so you can see it a bit better. So there's gas up here. Okay, P of the gas, where is it pushing? It's pushing down. Yeah, it's pushing down on the water, right? So there's water in here, and the pressure of the atmosphere is pushing out. Well, if the pressure of the atmosphere and the pressure of the gas were exactly the same, the water level would stay the water level, because the pressure inside of this graduated cylinder would be pushing just enough to keep the water level at the water level. But what if the pressure of the atmosphere was greater? What would it do to the water? It would push it up and in and up, right? So I'm going to draw the water blue now so you can see it a bit better. The water would then travel up here. And that would be a column of water, and that would be indicative of a higher atmospheric pressure than the gas pressure inside. Yeah, question. Okay, so we're going to see these different scenarios, but I just want you to be comfortable with trying to like finagle like who's greater, by how much, well how much in this case would be the height of the water in millimeters of mercury, even though it's not mercury, it's water. The last one is like this. So we have a huge, let me make this a little bit clearer. This is P gas. There's gas that has evolved inside of this big, huge bulb. And this right here is the mercury. Okay, what's pressure? What's out here? P atmosphere. Okay, it's pushing down. The pressure here is pushing in, pressing in. What can you conclude right now? They're the same because the heights are the same, right? P atmosphere equals P pressure. What if the pressures were different and the mercury went all the way up to here? Okay, so the P gas is pushing more, so P gas is equal to what? You know it's more than the atmosphere, right? So it's the atmosphere plus some, but plus what? The height. Good, that height difference, right? So we're going to say P ATM, P atmosphere, plus, here's my height difference. From here to here is height. So plus height, whatever that is in millimeters of mercury. So I could say, all right, guys, the atmospheric pressure of Concord, North Carolina is 720 millimeters of mercury. So this would be 720 millimeters of mercury. According to this diagram, what is the pressure of the gas if the height is 30 millimeters of mercury? Maybe 720 plus 30, so we would say the pressure of the gas is 750. So you can put numbers with this. Okay, so diagrams okay? They're kind of goofy looking, but we're going to use them in the lab. Okay, so back to where you were. You feel... Nope, this way. I don't know where my stuff is. You guys continue working on those. My people who do not get foldables, I have instructions and paper. And I'll put them over here, and you guys can come and grab it That we have anything on.
Otherwise, if 1 through 16 should be done on Monday as well as the concepts by 13.
Oh yeah. Give me a second. I need to finish homework.
Is that this? This is one.
You guys still have like almost 15 minutes. You plenty time to make sure you get your questions answered before you leave.
Let's have one. Read that.
I'm still going around to look at the PS13 and the homework you finished from yesterday, the worksheet.